quadratic table is 6.94U. That's the average, the weighted average, we call it. And it would be the weighted average of all isotopes. Lithium has two natural isotopes with atomic masses of 6.10512 and 7.01600 U. Calculate the percentage distribution between the two isotopes. So what we need to know is we need to know the percent lithium-6. How do I know that this one's lithium-6? Well, when I look at the actual mass, it's close to 6. And so if I have 6 protons and neutrons, it's going to come out close to 6U. So that's how I know that one. And this one's going to be percent lithium-7. So we don't know X, and we don't know Y. And so this is what we call a two unknown problem. When we have two unknowns, how do we solve it? Well, there are different methods we could use to solve it. I'll show you another method. Actually, when there's only two unknowns, there's a simple method for solving this, which I like to do. One way of solving this is by using two equations and two unknowns. Two equations for two unknowns. But we get hit with a lot of these problems. So as we get hit with a lot of these problems, I think there's a simpler way of solving it, because this involves a lot of algebraic manipulation. And so I think the simpler way of solving this is what I call the graphical method. The graphical method is not discussed in your book. So the two equations for two unknowns, you've done that, right, in algebra? So what would the two equations be? So equation one would just be our weighted average, Our weighted average is going to be just equal to the, I'd like to convert it into fractions. So I'll just say X percent lithium-6, and then we're going to convert it into a fraction by dividing it by 100%. And the percents cancel out, and we get the fractional abundance of lithium-6 times the mass of lithium-6, 6.10512 U, plus the fractional abundance of lithium-7, which I'll call Y percent lithium-7 divided by 100, because I want to convert it back into the fraction, 100%. And so the percents cancel. That gives me the fractional abundance of that, 7.01600 U. All right, that's equation one. What's equation two? So we're going to have to come up with another equation for this. And equation two is that all the isotopes have to add up to 100%. And so if there are only two isotopes, then those two isotopes need to add up to 100%. So if I take 8x% plus y%, that's going to give me 100%. Then all we do is we solve for one variable and substitute. It doesn't matter equation one or equation two. Probably equation two would be a lot easier. And so we solve for one variable and then substitute. So we could either solve for x or y. And then substitute in 1. I'm not going to do that because you've done this right before in algebra, in math, correct? Except that probably it wasn't so messy. It was probably a lot cleaner in algebra. You didn't have all these long numbers to deal with. They give us the weighted average. There would be 3 unknowns if we didn't have the weighted average. The weighted average is 6.94 U. So we know the first equation is equal to 6.94 U. Etc. So I'm just going to say etc. Now, for 2-component mixtures, we have a very simple way of doing this graphically. I already showed this to you visually. Visually, I showed this to you in this way for chlorine. There are 2 isotopes for chlorine. One isotope is 35, the other isotope is 37. If it were 50% 35, then what is the percent 37? 50%. If it's 75% 35, then what percent 37 is it? 25. And so that's what we do here. I just sent up a simple number scale. And so this is the graphical method, quite simplified. Let's say I'm going to go with 100% 37. That means if I have 100% 37, what is my percent 35? And what is my percent 37? And how much does it weigh? How much do the atoms weigh? About 37. The average. In other words, what would the average be? Closer to 35 or closer to 37? It'd be closer to 37. In fact, it would be if it's 100% 37, it would be 37. Correct? All right, now we do this. That's called an assumption. So we assume it's 100% 37 and the average is 37. Then we're going to take the opposite assumption. We're going to assume it's 100% 35. And so therefore, I'm going to get 100% 35. And what's my percent 37? 0%. And what's the average? The average is 35. So these are the 2 limits at the extreme. And then what I do is I just visualize this graphically. Scientists love to graph things. And so what I'm going to do is I'm going to graph this. I'm going to graph this in terms of percent 37. If I have 100% 37, what is the average? The average is 37, correct? If I have 100% 35, what is the average? 35. So I have 2 lines. Now this relationship should be linear. As the 37 decreases, the 35 increases, and as the 35 increases, the 37 decreases. So it's a linear seesaw relationship. We call the linear seesaw relationship a straight line relationship. A straight line relationship is, we could draw it like this. Oops, did I forget to unlock that? So what we end up with is a graph like this. Now, we can simplify this graph into a mathematical equation. So let's reduce this graph into the most concise definition we can generate. And what would that be? That would be y, which is the percent. Actually, what is it? Y is the average mass. So y is the average mass, which we call the average atomic mass, or just the atomic mass. People just forego the average and just call it the atomic mass. The atomic mass is equal to the slope. What is the slope? Delta y, which is going to be 2u, over delta X, which is going to be 100%, times the percent 37. So what did I call that? I called that Y percent 37, or this is X now, X percent 37. And so this will be chlorine 37, plus the intercept. The intercept is 35U, whatever that is. And so we come up with an equation like this. And so either we plug in the average atomic mass and calculate the percent chlorine 37, or we plug in the percent chlorine 37 and then calculate the average atomic mass. This works for mixtures of two. So this is what I did yesterday, but I just did it in my head. I did it in my head because I said, well, if it's 50%, it would be 36. If it's 25%, it's going to be 35.5. If it's 75%, it's going to be 36.5. So I just looked at this in my head and then figured that if the average is 35.5, it's got to be 25% 37, 75% 35. And so that's what I was doing when I was looking at the number line. Or you could just look at the number line and then write it here, which I did on the board yesterday. I didn't draw a graph yesterday. For this one, I'll just draw a graph. And so rather than doing this, which is more algebra than I want to do, I think this is less algebra. And so for the lithium problem, I'm going to do this. I'm going to assume 100% lithium 6. If I assume 100% lithium 6, then what's the average mass? The atomic mass would be 6.10512. And then we make the opposite assumption. And next, forget this and assume 100% lithium 7. And that comes out to 7.01600. And then I graph it. So I graph it based on the heavier one. So I'm going to put percent lithium 7 here, which is the heavier one, and I'll go 100%. This will give me a positive slope because if I'm at 100% lithium 7, I'm going to have an average mass of 7.01600 U. And then if I'm at 0% lithium 7, then I must be at 100% lithium 6, which is going to give me a mass of 6.10512. And then I just draw a line and assume it's a linear relationship here. And then I could figure out the equation for the line, y equals mx plus b, where y is the atomic mass, m is the slope, and so that's going to be 7.01600 U minus 6.10512 U. How many decimal places am I allowed in the subtraction? So 1, 2, 3, 4, 5. 5 decimal places here. 1, 2, 3, 4, 5 decimal places here. So in the answer in the numerator, I'm allowed 5 decimal places. So let's go ahead and calculate that to 5 decimal places. So I have 7.016 minus 6.10512. Let me do that again. 6.10512. I have a screen protector, so it's always not registering. 0.91088. That's 5, and then the 6 would be a 0. And this is going to be U. if I were to carry a sixth. So I had 6 sig figs here, 6 sig figs here, but my final answer is only going to have 5 sig figs. Oops, I'm not quite done yet. I need to clear out a little bit of space here. Okay, then delta x is easy. What is delta x? So this is my slope. I screwed this up for space. I don't have enough space here. And I just ran out of pages. Yeah, unfortunately, my Word is about to crash. I have to delete that, unfortunately. True. Unfortunately, I lost the earlier work. Let me jump straight to the equation. So y is the atomic mass, or the average atomic mass. And the slope was 0.9. Did somebody write it down?
Yeah, it was 0.91088
91088?
And then I think you wrote
A little
it was 6 or 0.
It was a little zero.
Yeah.
It was a little zero, but I'm not going to write it again.
And then it's just
We could do it either in lithium, in terms of percent lithium 6 or lithium 7. I chose lithium 7 because then that gives me a positive slope again. And then this is going to be times the, what we'll call X percent lithium 7 plus the intercept. The intercept is going to be 6.10512 U. So for me, this is less algebra, because all I'm going to do now is I'm just going to plug in my average atomic mass that was given. 6.94 U was the average that was given. And then solve for this. So I'm going to get X percent lithium 7 is going to equal 6.94 minus 6.10512. So 6.94 minus 6.10512 equals that. And then divided by the slope, which is, I haven't multiplied out the slope, so I'm just going to divide it by 0.91088 and then multiply by 100. And it comes out to 91.65. How many sig figs? We're only allowed 3 sig figs, so I'll just say 91.65% lithium 7. So if it's 91.65% lithium 7, then we can easily figure out what the Y percent of lithium 6 is. I think I got these backwards. It doesn't matter, X or Y. And Y percent lithium 6, well, this is just going to be 100, which is exact, minus 91.65%. And so this is going to give a 8.35%. And then at the very end, I round it, 91.7% lithium 7 and 8.4% lithium 6. They don't add up to 100. Why? They're supposed to add up to 100. Why don't they add up to 100? It's close. They add up to 100.1. Why isn't it at 100%? Rounding. What if I combine these two before rounding? What would it add up to? This adds up to 100%. So this is an example of rounding error. We try to avoid rounding error and I try to avoid rounding error by carrying extra digits to try to minimize it. And so this is why you sometimes see me carry extra digits more than I'm allowed, because over here I'm only allowed 3 sig figs, but I carried more. So when I check the answer, I don't know. Am I off because of rounding, or am I off because I made some kind of calculation error, like a calculator error, or am I off because I made some kind of conceptual error? And so if it's just a small amount, you're usually off due to a rounding error. But sometimes if you're overzealous with rounding, then you're off by a much more significant amount. So the percent error comes out quite high, and you start to wonder, did I do something wrong or what? So this is one way. Now we can double check this. The way we double check this is just to plug it back and go the other direction. We can double check this mentally. So for example, this is reasonable. If it's 92% lithium 7, then the mass should be closer to 7 than it is to 6. Is the average closer to 7 than it is to 6? Yeah, it's 694, which is pretty close to 7. So it seems conceptually it seems okay there, but if we want to really double check this, then what we do is we go ahead and calculate. I'm going to calculate the atomic mass and see. Atomic mass is supposed to be 6.94. Supposed to be 6.94. Am I going to get 6.94U? So we're going to plug it in. So I'm going to take the fractional abundance that I just calculated. Now what I'm going to do is, to avoid rounding error and confusing myself, I'm going to carry extra digits even though I'm not allowed. And so I'm going to go from percent to a fraction, so I have the fractional abundance. Your book likes to go to decimal, so going to decimal is 0.9165, which is probably better. But the thing is this. The way I think about calculations, I try to memorize the fewest manipulations, and then even though it takes me more steps to go through, I use familiar tools versus having a lot of different varieties. You know, sometimes I'll do it as a fraction, sometimes I'll do it as a decimal. No, you know, if you're going to do one, just stick with one. If you stick with one, then you're less prone to make mistakes. And so if you like decimal, converting to decimal form, convert it to decimal form, just fine. You know, decimal form is also a fraction. So if we convert this to decimal form, it's 0.9165, but that's actually a fraction because it's 0.9165 over 1. But the problem is people don't see this and use this as a conversion factor. When it's in a fractional form like this, we can easily do conversions using dimensional analysis. But when it's in a form like this, people have a harder time to connect it. When it's in a form like this, then it's easy to connect as a conversion factor here. For me, it's easy to connect. And so the mass is 6.10512. Or no, this is 90. What was it? 91 of lithium 7. So lithium 7's mass is 7.01600. Plus 8.35 over 100 times 6.10512. Since we're mixing rules for sig figs, we should do these calculations one at a time. So 91.65 divided by 100 times 7.016. How many sig figs am I allowed in this calculation? 4. So I have 6.430, and then I'm going to carry an extra 1. And so that's going to be 6.4301U. But that 1 I'm just carrying to try to minimize rounding error. Okay, let's do the other term here. 8.35 divided by 100 times 6.10512. How many sig figs am I allowed here? Actually, just 3 because of the 8.35, and so I just have 3 sig figs, maybe even. Correct. Yeah, that's correct. This is going to be 0.509, and then I'll carry an extra 1, 7. So how many decimal places am I allowed in the addition? 3. So I'll take this number plus 6.4301, and that gives me 6.9398U. And then I'm going to round this to 3 decimal places. What does this round to? 6.940U. Okay, so do they match? Yes. And so these percentages are correct. Like I said before, I think this is less algebra. And then in Chem 4, I think I assigned maybe about 3 problems like this that can be solved like this. In Chem 1A, there are a lot of problems that can be solved like this. And so you could either do this algebraically, or you could do this graphically. All right. Are there any other questions? Uh-huh.
What's the name of like this is it percent composition or something?
Yeah. Yeah, right. Percent composition of a multi-component mixture. Let me give you some examples of this. Like, for example, we want to figure out the percent composition of an iron ore. That is, how much of the ore is there and how much of filler. And the filler we don't have to analyze. We don't know. It could be a multi-component or it could be a 2-component mixture. And so that's something like we would do for this type of problem. And so you'd have 2 unknowns, and you can generate 2 equations, or you can do it graphically. The other one is like this. You have a mixture of a gas. Let's say the gas contains methane and propane. And what you want to do is you want to figure out how much methane is in there, how much propane is in there. And so both methane and propane will generate product, CO2, and depending on how much CO2 is produced, you can figure out how much, because methane doesn't produce exactly the same amount of CO2 as propane. They produce different amounts. So if you had, let's say, a pound of methane, you get a different amount of CO2 than if you had a pound of propane. So what we do is we assume that this is pure methane. How many pounds of propane, how many pounds of CO2 would we get? That's assumption 1. Assume 100% methane. Assumption 2, assume 100% propane. So if this mixture were 100% propane, how many pounds of CO2 would you get? And then you come up with a graph. And then you figure out how many pounds you actually got. Once you figure out how many pounds you actually got, then you know where you are in the position of the graph. And you can easily figure out the percentage. The alternative to that is generating 2 equations and 2 unknowns. The problem with 2 equations and 2 unknowns is, for the dimensional analysis for calculating the methane is going to involve a minimum of, let's say, 4 steps. And then the dimensional analysis for the propane is 4 steps. So your equations are starting to get bigger and bigger. And it becomes more and more of a pain to do this substitution and do all the algebra. It's not to say, it's not hard. I mean, it's not hard to do this. Here. I mean, this is not difficult. Because you've done it before. I mean, if you've done it before, you should be able to do it again. And so let's, finally. Let's do this really quick. The traditional way of solving 2 unknown problems is solving one of the equations for one variable and substituting that into the other equation, that particular equation. Looks like my Word is about to crash again, unfortunately. Okay. So the way I don't care how you solve it. It doesn't matter. I'd solve equation 2 for y%. We're calling y% lithium. So it's different from above. It doesn't matter what you label x or what you label y. But this is going to be 100% minus x% lithium 6. Okay, now we substitute. To make the substitution easier, I'm just going to call it y equals 100 minus x. And then I'm going to substitute in the original equation. In the original equation, I have 6.94, and then I have x here, which I'm going to leave the same. So this is going to be x over 100. I'm going to get rid of some of the units to make my life easier, and this is going to be 6.10512. The u's will just kind of cancel out. Plus, this is going to be 100 minus x over 100 times 7.01600. And then solve for x. So it's not terrible. It's just some algebra. Could you do this? Does this look pretty straightforward to you? Solving this equation for x? Pretty straightforward? Yeah, it's not that hard, right? So, well, 6.94 is equal to, I'm going to divide this right here and convert it. So this is going to be 0.0610512x plus, then I'm going to distribute this 100. So this is going to be 1 minus 1/100th x. So this is going to be 7.01600 and then minus 0.0701600x. And then put all the x's on one side and put all the others on the other side. And so maybe I'm going to subtract. Or actually, let's see. I'll subtract that and subtract this from both sides. So let's go ahead and combine the x terms here. Let's see if we get the same answer. Do you want me to do this or no? Yeah? All right. 0.0610512 minus 0.07016 minus 0.0091088 x, and then I'm going to subtract that from both sides. So 6.94 minus 7.016 minus 0.076. I can get rid of the negative signs here. And then I'm going to divide that by 0.0091088. 8.343%. That's my x. And therefore, the y is going to be 100 minus that. 91.656%. So my x was lithium 6 in this case, I think. Yeah, my x was lithium 6, and my y was lithium 7. And then I double check my answer. We always want to double check the answer if that. It's the atomic mass, which is supposed to be 6.94. That's a fact. This is supposed to be 6.94. Does it come out to 6.94? Well, we'll just plug these in. So it's 91.656 out of 100 parts of 7.016, 100 U, plus 8.343 out of 100 of 6.10512 U. And we know about doing the sig figs. When you do the sig figs, you got to do it separately, but I'm not, because I don't want to spend too much time on this. I've already probably spent too much time. So 7.016, 6.43. We're allowed, what, 4 sig figs maybe? Yeah, 4. plus 8.343 divided by 100 times 6.10512. Again, I'm allowed 3 decimal places. Which is going to round to so it checks out. So if you prefer doing it algebraically like this, that's fine. But I told you we're going to have different types of problems. Some we solve algebraically, some we solve using dimensional analysis, which is essentially algebra. Well, when I say algebraically, it's just by algebraic equations, and others we do by system of equations or graphical. And my preference is the graphical method if it's a 2-component. If you have a 3-component unknown, then that's more difficult because you need 3 equations to solve for 3 unknowns. But you've done a lot of these, right? A lot of 2 equation problems. Is that correct? Would you say? Mm-hmm. All right, any other questions? Oh, here they are. Shoot. All right, I'd like you to turn in this lab report next week, the laboratory burner. And so when we do the report, you're just going to fill out the report sheet here. The report sheet, some people have it backwards. Some people have it backwards in the sense that they make a mess out of the report sheet, but keep their lab notebook nice and neat. But you have to have it the opposite. You make the mess in your laboratory notebook, and you keep the report sheets nice and neat. The reports, these are supposed to make some kind of impact, make some kind of impression. And so if there are a bunch of mistakes on it, or whatever, it doesn't give a good impression. So they serve different purposes. Your lab notebook, the primary purpose of your lab notebook is for what? Yeah, it's to be the place where you store all your raw data. And from your raw data, you can generate reports easily. You can generate the reports from home, but you can't generate the raw data from home necessarily. And so the raw data, we need to make sure that we don't lose that, because that's what's going to allow us to write these reports. So raw data should be written in ink. However, report sheets, you can do these in pencil. It's not a problem as long as you have your original raw data in ink in your lab notebook. If you forget your lab notebook, then write it on loose leaf paper and then tape it or staple it or glue it to your lab notebook. And so you have a permanent source. for your raw data, a permanent record of your raw data. Now, the reports here, yeah, you want to try to keep these neat, and therefore, if you use pencil, it's not a big deal. If you make a mistake, just erase it. However, in your notebook, if you make a mistake, you can't erase it because it's in ink. So what we do in science is just cross it out. You cross it out with 1 or 2 lines or an X. And usually you leave the mistake legible so you can kind of figure out what you did in that particular mistake. You don't scribble it out to the point where you can't tell what the mistake is. Just cross it out. But one thing is, if you make a lot of mistakes on a page, what people like to do is they like to rip out the sheet because they want to keep their notebook nice and neat, but you don't have to rip out any sheets. In fact, ripping out sheets is considered a suspect. And it's poor lab technique. It's suspect because people don't trust why you're trying to hide data. Why would you try to hide data? Science is supposed to be open. We're not supposed to hide data. All the data should be open. People try to hide data maybe if they're in some kind of patent or some kind of invention claim. But anyway, let's finish this lab here. Why should the match be lighted before turning on the gas? So this is going back to the Bunsen burner. When we ignite the Bunsen burner, we want to turn the gas on first, or light the match first. We want to light the match first. Why? Mm-hmm. Yeah. Well, you can tell because there's a smell. Have you? Yeah. Methane is not poisonous. Yeah. Methane is. We don't have to worry. It's not going to poison you. But it could explode. Right. It could explode. Methane, it's not that you can't die. I mean, if we fill this room up with methane, it might push the air out and we'd asphyxiate ourselves. But also, if we filled this room up with methane, then we could have a fire or an explosion. And so, why should the match be lighted before turning on the gas? The reason is to minimize the amount of methane that escapes into the room. And so if we light the match first, then we can make sure we combust all the methane and none of it escapes. So this is the normal way we light it. Sometimes it's hard to do depending on how it was set before. And so, there. Versus, well, I think I've done this many times where I turned on the gas and then had trouble striking the match, but the gas is leaking out into the room, and then pretty soon you smell the methane in the room. And if that concentration builds up high enough, then that's definitely a fire explosion hazard. Why must the methane be mixed with the air in the barrel before it is burned? Does somebody have the answer for that? Uh-huh. Yeah, so we get complete combustion. We need enough air in there, and if we don't pre-mix it, then we don't have enough air. And if we don't have enough air, what color is the flame? Yeah, yellow, orange. And so why must the methane be mixed with the air in the barrel before it is burned? Because if it isn't mixed, then we get a yellow flame, which indicates a lack of oxygen. So that's something we could do. We could just remove the barrel entirely. And then a little strong the flame is. A little weak. It's not bad. Do you see that? A little bit of yellow. There's a lot more yellow. I don't want to leave a yellow flame like that for very long. Why? Hmm? It might blow out. But even a blue flame could blow out. I don't want to leave a yellow flame like that for very long because it's producing products of incomplete combustion. The yellow comes from what? Soot. But in addition to soot, I expect what else to form? Carbon monoxide. And so if you have like a gas heater, let's say the air fuel mixture gets messed up like this. Let's say the air intakes get clogged on your home heater. Then you also get a lot of, in addition to soot, you also get a lot of what? Carbon monoxide. And so do you know how many carbon monoxide deaths there are per year in the U.S.? Not that many. It's going down. $1,244 people died in 2022. 624 were accidental, and 579 were suicides. So this is, yeah, this could be easily prevented. And so they recommend having a carbon monoxide detector, which we do have, but ours has a pretty high limit to trigger. But if you have a home one, those are pretty sensitive. So if your burner is not burning correctly, it's not getting enough oxygen, then you can tell. What is the color of the flame when the air inlet holes are closed? Where are the air inlet holes? At the bottom of the barrel. Somebody asked me that the other day. Right, right. The gas comes out of this little nozzle here, the orifice, and the air is going to come from the side, and then we can mix them together in the barrel. The purpose of the barrel is to mix the gas, methane, with air, oxygen. What is required to convert the cooler luminous flame? Is it the blue flame that's luminous or the orange flame that's luminous? It's the orange flame. We call that luminous. When it's blue, it's hard to see with the room lights on. But the yellow or the orange flame is a lot easier to see. And so what is required to convert the yellow flame to a hotter flame? Oxygen. More oxygen. More air. Draw a diagram of the non-luminous flame, the blue flame, using your results from the Flint test. The Flint test is a match test we did earlier. Label the hottest and coolest parts of the flame. So here we just sketch a burner. You can just draw the top of the burner like this. And this should be a nice blue flame. What's the structure of the flame? Like a good flame? Cone. We want a cone. And then there's going to be an envelope of a flame around the cone. Like this. There are 3 zones here. The 3 zones are inside the cone, the surface of the cone, and outside the cone here. Which is the hottest zone? Yeah, on the surface of the cone. A lot of people will say the tip of the cone is the hottest. But anywhere on the surface of this cone is going to be very hot. Where's the coolest part of the flame? The inside of the cone. Here we have unburnt gases. So here we have unreacted methane and air. And then outside, this is like the medium part of the flame. What was that again? Oh, because it hasn't ignited. And so the gas in here is all unburnt. So this is just methane and air. When it hits the surface of the cone is where it gets ignited and reacts. But inside the cone, it's still unreacted, just a mixture of gases. It hasn't started reacting yet. Quickly. No, the surface of this cone is hot. And so the entire surface of this cone is extremely hot. People just say the top because heat rises and then the heat is focused there at that pinpoint. And so it's more concentrated. What is the condensate that forms inside the beaker when it is held above the flame? Water? Do you guys remember this? Water is correct. So I have a non-luminous flame. Can you see it? And then I'm going to take a beaker and I'm going to hold it above and then watch the inside surface of the beaker. Do you see what's happening? Did you see it fog up? Let me cool it down. Once it gets warm enough, then the fog evaporates. Let's try it again. Do you see the fog inside the beaker? Yeah? Okay. What's happening is steam. Steam is being produced in the flame, and when the steam touches the cold surface, then it's going to condense into liquid water. And so what is the condensate that forms inside the beaker? Water, liquid water. Where does the condensate come from? The air doesn't have that much water in there. Where the water comes from, it comes from the chemical reaction. If you recall, methane has the formula CH4. And since it's a gas, we put this little G here. And so this is methane gas. And then we're reacting it with what? Oxygen and air. Oxygen and air is O2, that's correct. And that would be a gas. But what forms from this? This is a combustion reaction. Carbon dioxide. Which has the formula CO2 and not hydrogen. And water. So one way of thinking about this is when we oxidize methane, we form an oxide of carbon, CO2. Do you know another oxide of carbon? Carbonate, yeah. How about another one? The one that we don't want to form. Otherwise, we might end up accidentally killing ourselves. Carbon monoxide. That would be another oxide. And an oxide of hydrogen. What's an oxide of hydrogen? Hydroxide or water. Water is an oxide of hydrogen. And so this process is, what we're doing is we're oxidizing the methane or combusting the methane. And one of the best oxidizers around is oxygen. And the great thing about oxygen is it's free. Do you have to pay for it? No. Right now you don't have to pay for it, but maybe somebody will devise some kind of tax system to tax the air that you breathe. Can you imagine that? They haven't yet devised a tax for the oxygen, but they have devised a tax for the carbon dioxide. Do you know there's a tax for carbon dioxide? Yeah, it's called the carbon tax. And this is the reason why, they want to get rid of. Pretty soon we won't have Bunsen burners. Pretty soon we'll have electric burners. We already have electric burners, but we'll have to have an electric burner substitute for our Bunsen burner. Because on the one hand, maybe it's better because there'll be fewer accidental carbon monoxide deaths, electric. Yeah, it's a product of the chemical reaction. Water is a product of the chemical reaction. But what is the problem? Why do they want to tax CO2? Do you know the reason? Actually, you're already paying a tax for CO2 because do you know how the electricity is produced to power your electric vehicle or electric heater? Most of the electricity in California is produced from combustion of not coal. Coal's on the East Coast, so most of the electricity on the East Coast is produced. Or even Utah. Utah has big coal reserves. Idaho has a lot of coal. And so there are a lot of places that burn coal for electricity. In California, we burn methane, which is a lot cleaner than burning coal. But still, you have to pay the carbon tax for that. And so we're already paying carbon tax in our electricity rates. But the reason why they want to get rid of CO2 is because global warming. Right? And so are you familiar with global warming? So they want to cut down the CO2. CO2 is a gas, liquid, or solid? Gas, yeah. But CO2 is a lot better than the other one. Let's look at the oxides of carbon, which we can call COX. One of the oxides of carbon is this one, which we call carbon monoxide. Carbon monoxide has other names that we could use for it, that people might be able to figure out what it is. What's the normal charge on oxide? 2-. So if oxygen is 2-, then what does that make carbon? Because carbon monoxide is neutral, so it has to add up to 0. So if I take X, which is carbon, plus a -2, which is oxygen, this has to add up to 0. So X must be 2+. So what we could do is we could call this carbon 2 oxide. Carbon 2 indicating the what we call the apparent charge on carbon. It's +2. +2 is fairly common, what we call oxidation state for carbon. If we look at the Sargent-Welch, which I have probably open, but I don't know which tab it's under. Wow, this is really blurry. This is off the Sargent-Welch website. But do you see carbon here? Do you see the above there? It's plus or -2, +4, -4. Can you see that? What does that refer to? Yeah, the possible charges. And we don't call them ions because sometimes they don't sit as, you know, when we normally think of ions, they stand alone, but carbon needs the oxygen to pair up with it. Otherwise, it's kind of unstable. And so on your list of monatomic cations, you didn't find carbon with a +2, and you didn't find carbon with a +4 because it has to pair up with something to be stable. And so we'll call this carbon 2 oxide. That's another name, but for sure the common name is carbon monoxide. Then I might go like this. I might go, is carbon monoxide, yeah, that's potential global warming, but it's also very poisonous, so we don't want to make it. What if I made, let's say I just oxidize this a little bit more. Let's say rather than carbon monoxide, I made carbon 1.1 oxide. You know, so a little bit more oxygen. Maybe that makes it safer, you know. Just a little bit more air, but not too much air. Is that going to be safer? Yeah, maybe not. Let's add a little bit more. Maybe I'm going to go carbon 1.15 oxide. How about that? Does that look good to you? How about 1.1513, whatever, 153? How about that? 1.153. Is that safer? And what do you? How do you name this? Right. This would be a violation of what law? This would be a violation of the law of multiple proportions. So I don't have to worry about naming that, fortunately. Because that would be kind of a pain to name, wouldn't it? But you do have to name this. This one we call CO2. This one is the next one, which would be carbon dioxide for 2 oxygens. Or what's another name for carbon dioxide? The other name would be if oxygen is -2, how many of those do I have now? And so I would have X for the carbon plus 2 times -2 for the oxygen. Since I have 2 at -2, this has got to equal 0. All compounds are neutral. Ions have a charge, compounds are neutral. And therefore X is what? 4. So the other name for this is carbon 4 oxide. But we don't really call it carbon 4 oxide. We call it carbon dioxide. But if somebody called it carbon 4 oxide, you probably know what they're talking about. They're talking about this. Okay, let's continue this. What would you name this? Well, this is easy to name. This would be called carbon for 3 oxide, carbon trioxide. What would be another name for carbon trioxide? Well, if carbon is X, and then I have 3 oxygens at -2, 3 oxides, this has to add up to 0 because compounds are neutral. And we'd call this, what would X be? +6. and we call this carbon 6, Roman numeral 6. Surely, if carbon dioxide is a bad greenhouse gas, then carbon trioxide must be worse. Correct? Hmm? But the taxes on carbon dioxide, why aren't they taxing carbon trioxide? They should also tax carbon trioxide, don't you think? But they don't have to worry about taxing carbon trioxide. We don't have to worry about carbon trioxide. Why? Hmm? It's not what? As useful? Yeah. That's true. It's not as useful. Hmm? Yeah. We don't expect any carbon trioxide to come out of the combustion process. In fact, they don't have to worry about regulating carbon trioxide because we wouldn't expect it to form. Why wouldn't we expect it to form? Because carbon doesn't have what? It doesn't. This carbon is not 3 minus. This carbon is plus. No. If we have 3 oxygens, there's another way of visualizing this. And so if this algebra doesn't work, you can visualize it like this. We have 3 oxygens. Each oxygen is an oxide at minus 2, or 2 minus. And so that gives us a total of minus 6. Now the carbon is plus X. And so plus X plus a minus 6 has to add up to 0 because carbon trioxide is neutral. And therefore X is plus 6. So we could call it carbon 6 oxide. Uh-huh. Yeah, there's certain patterns in nature. One of the patterns in nature deals with the periodic table. So it's kind of what you say, you know. Okay, I guess this did crash. What is the charge range for carbon? +4 to -4. If we go outside that range, it becomes exceptionally unstable, and it's not likely to form. And if it does form, it's going to be very short-lived. And so what we say is, if it's +6, is that within the +4 to -4 range? No. And so how did you figure out the +4 to -4 range? Well, how we figured that out is based on this. The +4 comes from carbon losing 4 electrons. So carbon, when we look at it, carbon has how many protons? 6 protons. And that means it's going to have 6 electrons if it's neutral, and then it's going to have some number of neutrons. We don't know how many neutrons because it depends on the isotope. So carbon normally has 6 electrons and it carries a 0 charge. Now what we want to do is we want to look at the nearest noble gases. Neon is 10, helium is 2. And it turns out the pattern in reactivity is it could go up to neon, it doesn't go beyond that, or it could go down to helium, but doesn't go beyond that. And so to go from 6 to 10 electrons, we have to gain 4 electrons. So if I gain 4 electrons, I end up with 10 electrons. If I end up with 10 electrons and I have 6 protons, what's the charge? And so each proton's plus 1, each electron's minus 1. So this is a plus 6 plus a minus 10. A plus 6 plus a minus 10 gives us minus 4. And so if we go up to 10 electrons, the carbon is going to have a minus 4 or 4 minus charge. That would be at one end of the extreme. We don't expect to go to minus 5. We don't expect to go to minus 5 because that would be highly unstable. And it wouldn't exist. Or it could go all the way down to 4 electrons. To go from 6 electrons to 4 electrons, how many would I have to lose? So to go from 6 to 4, I'd have to lose 4 electrons. 6 to 2, sorry. And that leaves me with 2 electrons here. And I still have 6 protons. So if I have plus 6 plus a minus 2, what's the charge? Plus 4. So this gives me my carbon plus 4. Now plus 4 or minus 4 are very difficult to achieve. So oftentimes we show this with a Roman numeral. And so this would be carbon Roman numeral 4, or this would be carbon Roman numeral minus 4, let's say. Or we'll just call it carbon 4 on this side. So do you see where the plus 4 and minus 4 come from? Yeah? Pretty much? That's expected range. So we don't expect carbon trioxide. However, we might see something like this. What is the name of this? This is a polyatomic oxygen off the periodic table. So let's go back to the periodic table and take a look. Actually, we started at 2:30, huh? It's time for a break, so let's take a break right now, and then we'll come back and take a look at this one. So you don't have to worry about carbon trioxide. We predict that carbon trioxide shouldn't exist. How about this one, though? Is this called carbon trioxide 2? And so this is a polyatomic oxyanion. And so what we do is we use the periodic table. Since it's been a while, let's go back and review this here. So for polyatomic oxyanions, we memorize the 8s. So which 8 do you have memorized off the periodic table here? You should have this one memorized, borate. What's the formula for borate? BO3, 3 minus. The 8s have historically been the most oxidized. And so like borate, what's the range of charge for borate? Borate can either gain how many to go to 10 or lose how many to go to 5. I mean, not to go to 5, sorry. Go to 2. Okay, plus 5 electrons. Each electron's minus 1. So that gives boron a charge range from minus 5, if it gains 5 electrons, to go to 10. Or it could lose how many to go to 2? 3. So that would give it plus 3. If we lose 3 electrons, then we lost 3 negative charges, but we still have the same number of protons. So the proton to electron ratio is no longer balanced. In the case for borate, it's easier to lose, right? Because it's closer. And so boron, the max positive charge is plus 3. What is the charge on boron in borate? Well, we could figure this out. Let's maybe make us some more room here. BO3, 3 minus. So the way we do it is, how many borons do I have? I have 1 boron at X charge plus 3 oxygens at what charge? Minus 2. This has got to equal, in this case, this is not a compound. Compounds are neutral. This is an ion. And ions are not neutral, and so this has to add up to the net charge of minus 3, which we get there. So what is X? Plus 3. And so the 8s have traditionally been the most oxidized, and these are the ones we find in nature. So borates have a history in California. There's a town called Boron. Have you heard of it there? And there's borax. I don't know if you've ever used borax soap. Have you ever used borax soap? For people, yeah, if you make slime, then you're going to use it. So you've used borates before. That's because of the environment we live in. When we look at the atmosphere hasn't always been like this. The atmosphere has changed over time. You know? And then that happens naturally over time through geologic processes. And then there's the human process that people are worried about. People are worried about the global warming. But you might be surprised. We live in a very oxidizing atmosphere. We live in a very oxidizing atmosphere because air consists of what percentage oxygen? Over 20%. It's like 21, 22% oxygen. And so things tend to get oxidized. And so a lot of elements are in the form of oxides on the surface of the Earth. So there aren't like boron deposits, they're borate deposits. There aren't carbon deposits, there are carbonate deposits. And usually what we see is that things will get oxidized to their max. And the max for boron is plus 3. And then we stop. But interestingly, the atmosphere has fluctuated. You know, at one time in geologic history, the atmosphere used to be a reducing environment. In a reducing environment, you know, the iron wouldn't rust. And so you could find iron deposits at some depth, you know, buried under a whole bunch of other rocks. Or you could find like rust deposits, you know, when the atmosphere changed to more oxidizing atmosphere. So the levels of oxygen have fluctuated in the atmosphere. But we need this level of oxygen. If the level of oxygen goes lower, then that's big trouble, for sure. All right, so you memorize borate. What's carbonate? CO3, 2 minus is the charge. So that's carbonate. What's nitrate? NO3, good. Charge? -1 is correct. There's a pattern there. Well, your next nomenclature test is going to be a lot more things to either have memorized or a lot more things that you should be able to figure out. So, for example, here I would memorize borate and then figure out carbonate and nitrate. So that would lessen the memorization load. But these are also maxed out. So if I look at carbonate, which I was asking about earlier, we don't expect carbon trioxide, but we do expect carbonate. Why? Well, what is the charge on carbon? And so we have 1 carbon at X plus 3 oxygens at -2 have to add up to a net charge of -2. So what is X? Plus 4. So we expect that. So carbonate's maxed out at plus 4. So we don't have to worry about, let's say, is there something that's CO 2.9? Would you expect a CO 2.9 2- to exist? No. Unfortunately, we have atoms to thank for that, because if we didn't have atoms, then things could happen in any ratio, right? Unfortunately, we have the law of, what was the law? Of multiple proportions. Do you see how the law of multiple proportions and the whole concept of atoms easily explains these ratios here? Normally, it's maxed out. So, for example, nitrate. What's the charge range for nitrate? Oh, not nitrate. What's the charge range for nitrogen, let's say? Nitrogen should range from, well, it's 7. So if we're at 7, we can go to 10 by gaining 3, so that's -3. And so nitrogen -3 is called nitride. Or it could go all the way down to 2, which means losing 5 electrons. If we lose 5 negative charges, then we're at plus. So, if we lose 5 negative charges and the positive charges stay the same, then we're going to be at plus 5. And so nitrogen is going to vary from plus 5 to -3. Do you see the pattern there? Yes? No? So to go from 7 to 10, we have to add 3 electrons. If we add 3 electrons, that's 3 negative charges. So that means we're going to have 3 extra negative charges. If we go from 7 all the way to 2 here, that's losing 5. If we lose 5 electrons, then that's losing 5 negative charges, which means the 5 positive charges are going to be imbalanced. So this is plus 5. The number of protons stays the same. In other words, what we could do is this. Nitrogen with a plus 5 has 7 protons, and how many electrons? 2 electrons. So if you take 7 protons and 2 electrons, what's the net charge? So a proton is positive, an electron is negative. So this is plus 7 minus 2 gives us plus 5. So that's where the plus 5 comes from. And then the -3 comes from, we have 7 protons, but in this case, we're gaining 3 more electrons. So altogether, we're going to have 10 electrons, like neon. So when we have 7 protons plus 10 electrons like neon, what's the charge? -3. Do you see that? Yes? No? Could you figure it out yourself? All right, good. Well, we live in an oxidizing environment, so nitrogen in nature is typically found as nitrate. Although we have nitrogen gas here, but there are a lot of nitrates. So if we look at nitrate, let's take a quick look at what the charge is on nitrate, just as a side example here. So nitrate is NO3 minus, And so we have 1 nitrogen at X charge plus 3 oxygens at -2. This has to add up to a net charge of -1. And therefore X is +5. So we live in an oxidizing environment, but the strength varies. For example, the concentration of oxygen in air is only 21, 22%. But what if we went to 100% oxygen? Is 100% oxygen good? I don't know. In fact, they say that if you go above what percentage? They say you don't want to breathe above a certain percentage because we're not adapted for that particular percentage. I read it. I forgot the number. Let me take a look at the number. This is from studies. Is people want, have you heard of hypobaric and hyperbaric and that kind of stuff? For human breathing. OSHA, which is Occupational Safety Hazard Association, or whatever. This is a government agency that regulates safety, including the safety in our lab here. OSHA lists the safe max percentage of oxygen as being 23.5%. Very high levels of oxygen can cause oxidizing free radicals to form. These free radicals attack the tissue and cells of the body and cause muscle twitching. The effects from short-term exposure can most likely be reversed, but lengthy exposure can cause death. So we don't, like I said, the level of oxygen is varied in the atmosphere over geologic time. So things can become more oxidizing, less oxidizing. Under these conditions, we have this level of oxidation, but an interesting thing happens. And that interesting thing that happens is for this particular species, chlorine. What's the range of charges that you expect for chlorine? So we look, chlorine is element number 17, and then we look at the nearest noble gases. The nearest noble gas here is 18. To go from 17 to 18, how many more electrons do we want? Just 1 electron, and that means chlorine's charge will range from -1, which is chloride. But I could also go the opposite direction and go to 10. I wouldn't go all the way to 2, that's too far away. But if I go to 10, that's the next nearest one. If I go to 10, how many do I lose? 7, so that's -7 electrons. And that would mean chlorine would have a positive charge of +7. So the range we would expect for chlorine would be from +7 to -1. But think about it, losing 7 electrons, that's a lot of electrons to lose. And when we lose electrons, that's not so easy to do. And so this is what we expect. We'd expect chlorate to be maxed out because, it's in an oxidizing atmosphere. We live in an oxidizing atmosphere which contains about 22% oxygen. But it's not enough. Because what is chlorate? Tell me the formula for chlorate. ClO. Charge? 1. +1 or -1? This is chlorate here. Has chlorate been maxed out? Let's take a look. We have 1 chlorine at X plus 3 oxygens at -2. This has to add up to -1. What is X? +5. Has it been maxed out? No. So under normal oxidizing atmosphere, our normal oxidizing atmosphere maybe will form chlorate rather than, but chlorate, well, that's usually what forms under these types of conditions, but it hasn't been maxed out. So we need a little bit more extreme conditions. And so under a little bit more extreme conditions, we could form, what's the next higher level from chlorate? The next higher level is ClO4 minus. Would you expect ClO4 minus to exist? Let's take a look. We have 1 chlorine at X plus 4 oxygens at -2. This has to add up to -1. What is X? X is +7. So do we expect this to form? Potentially? Is this within the range? That's what I'm asking. Is it within the range of -1 to +7? This is maxed out. So this is maxed out, but normally when it's maxed out, we call it 8. Now we've run out. You know, normally like carbonate, nitrate, that's maxed out. Borate's maxed out. But chlorate is not maxed out. And so we have to do something else. We have to come up with a new idea. What's the new idea? We're going to call it perchlorate. And so per comes from hyper. You know hyper? Hyper means more, right? And so this is hyperchlorate. Or hyper sounds funny, so we just shorten it to, rather than calling it hyper, we call it per. And we have to do this for chlorate because chlorate hasn't been maxed out. Now, let me ask you this. We know that perchlorate exists. How about percarbonate? Does percarbonate exist? No. How about pernitrate? Does pernitrate exist? No. Why? Because those are maxed out already. And so for chlorate, we have to add one more. It's kind of ad hoc after the fact. Oops, we didn't quite max it out. We can have one more higher.
Can you explain how that's related to the atmosphere? Like, why couldn't we just think of ClO4 chloride?
Because we have different kinds of conditions. So you could have like what we call mildly oxidizing conditions, or you could have strongly oxidizing conditions. And the conditions that we live under aren't strong enough to oxidize chlorine to the next higher level. And so what we have to do is we have to adjust the conditions. We could have more oxygen rather, you know. If we have more oxygen, yeah. Let's say we did it in 100% oxygen, then probably we'd get perchlorate rather than chlorate. But we're only at 22% oxygen in air.
So you're saying that in nature, like as it is right now, it doesn't really happen, and we have to make it like artificially made.
Yes, it's artificially made because it's unstable. In nature, you could find chlorates, but you won't find perchlorates. You'd have to make it yourself. In nature, we find lots of nitrates, but would you find any pernitrates? No. But could you make any pernitrates? No.
So are the ions that end in H have to do with like nature?
Yes, exactly. The ions. A lot of these were named before. You know, some stuff. So this just comes from historical. You got these geologists looking at different minerals, and minerals are compounds, pure substances. Minerals. Rocks are mixtures of minerals and that kind of stuff. So you have a lot of geologists looking at minerals, and you have a lot of carbonate minerals out there. There are lots of carbonates, you know. But are there lots of carbonate minerals? You know, no. So the eights usually come from like nature. In the ites, you know, the ites, if you're in the oxidizing environment, eventually the ites are going to be converted into eights, you know. In other words, this is like rusting. We live in an environment where things are always being oxidized. And so when I do nomenclature, I start with the 8s. Because the 8s are the most common. All right, not only do we have to worry about the law of multiple proportions, but there was another law that we got to concern ourselves with. And what was that other law? A couple of laws. Another law was the law of conservation of mass and the law of constant composition. So for example, if I wanted to oxidize carbon just a little bit more, I might say, could I go to CO2.1? Is that possible? No. And so we have the law of constant composition. All CO2 is going to have this, all H2O will have this composition, etc. And then we have to worry about the law of conservation of mass. And that means that we cannot lose or create atoms. And so let's count the atoms here. We start off with one carbon atom here. We end up with one carbon atom here. Over here we start off with 4 hydrogens, but over here we end up with how many hydrogens? 2 hydrogens. So 2 hydrogens have disappeared. Since 2 hydrogens have disappeared, I can fix that. I'm going to make water with H4O. If I make water H4O, then I take care of the 2 missing hydrogens. Is that possible to do? No, because water is fixed composition, law of constant composition, so H4O is not going to work. And so how can I fix that? How I can fix that is I can just make 2 waters rather than 1 water. And that's called balancing. That's correct. And so now I have 4 hydrogens. And then look at the oxygens. How many oxygens do I have on the left? I have 2 oxygens on the left. On the right I have 4. 2 from the CO2, and then I have 2 waters. Each water has 1. And that gives me a total of 4. So should I make oxygen O4 rather than O2, or how should I do this? Does O4 even exist? No. And so how do I fix it? Yeah, I'm going to put 2 O2s. And so this is what we call a balanced reaction. Now in the flame, I produce H2O, solid, liquid, or gas. In the flame, gas. But the situation is, it doesn't stay gas forever. What happens when that steam hits a room temperature surface? It's going to condense back to a liquid. And so this doesn't stay hot forever. It's going to condense back to a liquid. And the reason we want to wait until it condenses back to a liquid is this. If you take liquid water and boil it, you have to add energy. But if you take steam and condense it, do you know what happens? Energy is released. In other words, you need a refrigerator, you need a cool surface to absorb that energy. So there's one more thing we have to conserve, and that's energy. So I'm going to put energy out here. And so we're going to wait for the water. And so to answer the question, the water comes from combustion. It's a product of combustion. And so water is a product of combustion. And so what are we combusting? We're combusting this. Methane burns very cleanly. The only problem with methane is carbon monoxide, soot, but you can get rid of those by properly adjusting the air to gas or fuel ratio. And CO2. CO2 is a problem because CO2 is a greenhouse gas. And we try to minimize the emission of that. But the problem is this. I think rather than getting rid of this entirely, one thing we could do is we could sequester or capture the CO2. And there are lots of ways that CO2 can be captured. Some of these are kind of far out, and some of these are kind of scary. One person, they propose, you know what they propose doing with the CO2? They want to pump it deep under the ocean. And so deep under the ocean, there's high pressures and low temperatures. And what they want to do is they want to condense the gaseous CO2 to make liquid CO2. And so they're going to have little bubbles of liquid CO2 deep under the ocean. But you know what kind of scares me with that? Because what scares me is if there's an earthquake and let's say all that CO2 comes up. And then as the CO2 comes up, it's going to push all the air out. And even though CO2 is not so deadly, if there's no air, we can't breathe. And if we can't breathe, we'll end up dying from asphyxiation. So we have to worry about that. But there are other ways of capturing CO2. The only problem is they're kind of expensive. But maybe people will do that. The best thing would be to capture the CO2 and then convert the CO2 into usable chemicals. So there are people who are trying to convert CO2 into alcohols, because alcohols can be used to make other things. Or they can be used just as alcohols alone. All right, so here, this is methane. Methane is what we call organic nomenclature. Organic nomenclature we might touch on a little bit later. Meth stands for one carbon. Ane stands for all what we call single bonds, which we talk about later. We aren't doing any organic, and so we call this a common name, and you just kind of memorize this. But there are other names for this. Methane is what we call a binary molecular compound. And for binary molecular compounds, we have a set of rules. Now, these aren't laws. The difference between a law and a rule is rules can be broken much more frequently than you should be able to break laws. And so there are going to be a lot of exceptions to rules. So when we look at binary molecular compounds, first, what is a binary? Binary is two different elements. Molecular is a compound of nonmetals. And so binary is two elements. Molecular are nonmetals. Nonmetals typically form molecules, and so that's why we say carbon's a nonmetal, hydrogen's a nonmetal. The metal's on the left side of the periodic table, the nonmetal's on the right side of the periodic table. When we have binary molecular compounds, then we have a set of rules. The rules, we would call this carbon tetra. Tetra is the prefix for 4, hydride. So this, using the rules for binary molecular compounds, would be called carbon tetrahydride. So this is an alternate name for methane. But it also depends on how you want to name this. We could also name this like this. We could also name this hydrogen carbide. That would be an alternate name. Or another name for this could be carbon tetrahydride. This would probably be better up here. I'll call this carbon, Roman numeral 4, hydride. That would be correlated with this here. And down here, we could call this instead of hydrogen carbide, we could call this hydrogen carbide. That would be it. And so these are potential alternate names for methane. But the main name that we use is methane. Oxygen is a little bit tricky because when somebody says oxygen, you don't know what they're talking about. So when somebody says oxygen, there are two things that come to mind. One is atomic oxygen. Atomic oxygen is just O. 2 is molecular oxygen. Molecular oxygen Molecular oxygen is O2. So when somebody says oxygen, you don't know if they're talking about atomic oxygen or molecular oxygen. And so sometimes that requires clarification. So if somebody says oxygen in the air, then you already know. If somebody says oxygen in the air, you know they're talking about molecular. But if somebody said how much oxygen is in carbon monoxide, then you'd be thinking, how much oxygen is in carbon monoxide? How much oxygen is in water? You would be thinking atomic oxygen. How much oxygen is in nitrate? You're thinking atomic oxygen, not molecular. And so by the context of how they phrase it, then you can get an idea, but sometimes you just don't know. In this case, we would know. How about oxide? If somebody said oxygen, would you think oxide? No, because we don't call O2 minus oxygen, we call it oxide. And so this wouldn't work here. CO2, is this a binary molecular compound? Yes or no? Binary, 2 elements. Yes or no? Binary. Yes. Molecular consists of nonmetals. Are both of these nonmetals? Carbon's not a metal. The metals are on the left. There's a dividing line. I think I talked about the metalloids, right? The transition. And the answer is yes. This is a binary molecular compound. For binary molecular compound, we name it according to the rule. The rule would be carbon dioxide. And so according to the rule, we should name this carbon dioxide. There are other ways to name this, though. Another way of naming this is like this. What is the charge on carbon in carbon dioxide? Positive 4. So we could call this carbon, Roman numeral 4, oxide. And so that would be called carbon 4 oxide. What would carbon monoxide be called? Carbon monoxide would be called carbon 2 oxide. This one we use the common name. The common name for this is water. However, is this a binary molecular compound? Yes. And so, according to the rules, we would name it dihydrogen monoxide. But nobody calls it dihydrogen monoxide. Everybody calls it water. Another name for this would be hydrogen oxide. But I'm not going to write it there. And yet there are more names for this. All right, so what is the condensate that forms inside the beaker when it is held above the flame? Water. Where does the condensate come from? Product of combustion. Why should cut glass or chipped glassware always be fire polished before using for other purposes? Excuse me. When you get a chip or break in glass, it forms sharp edges. This is why you're not supposed to wear sandals in lab. If you wear sandals in lab, there could be broken glass on the floor and you might cut or get a glass shard in your foot. But let's say if there's a chip or a crack, we normally throw it away. But let's say it's just a small chip, but there's a sharp edge. If it's just a small chip and there's a sharp edge, what we do is we throw it in the burner. We put it on the hottest part of the flame. What's the hottest part of the flame? The tip of the cone, and we wait. Eventually what happens is the glass softens. As the glass softens, it's going to dull the edge. And that's called fire polishing. And so all we're going to do is melt the glass a little bit, soften it. We used to have a lab for this, and that's why there's instructor approval, but I guess the majority of Chem 4 instructors decided they didn't want to do that anymore, so we don't do it anymore, but that's just for your information. All right, now on the back of this report is the feedback quiz. It's just true or false, but there's one additional thing you have to do. If it is false, you have to change the underlined word to make it true. So let's take a look at number 1. Natural gas turns out to be a mixture. It's a mixture of methane and other gases. So this is an example of where we use the 2 equation, 2 unknown type stuff, to figure out the composition of this mixture. But I'm not going to worry about the composition of the mixture. It's primarily the chemical, what? Methane. Is that true or false? This is true. So we don't have to do anything. 2, the purpose of the burner is to mix fuel, the methane, with the nitrogen and air. That's false. So I'd mark that false. But in addition to marking that false, I have to change the underlined word, nitrogen here. And so what would I change that to? Oxygen. Good. To change it, just draw a line through there and write oxygen below. Does this make sense? Okay. So you can work on these and then turn this in next week. If you have any questions on them, I can answer that. But what I want to do is I want to continue with nomenclature. And so let's continue our discussion of nomenclature, which is chapter 6. The first type of compounds we're going to look at, well, we know the elements. Do you guys know the nomenclature of the elements? Yeah, I think we talked about it. Let's look at nomenclature of compounds, primarily. And so the first are the binary molecular compounds, where we're going to have element A and element B in some ratio. We'll call it X to Y ratio. What we're going to use for X and Y is we're going to use the prefix system in the name. So if X or Y is 1, what do we use as a prefix? Mono for 1. If X or Y is 2, then we're going to use di as a prefix. 3, tri. 4, tetra. 5, penta. 6, hexa. 7, hepta. H-E-P-T-A. 8, octa. 9, nona. 10, deca. 11, 12. We'll stop here. We'll say etc. I had to know up to 20, 30, up to 30. But I forgot it. I don't really use it that much. Like dodeca 12, ico 20, etc. That's not for binary molecular compounds. It was for organic chemistry. I was looking at fatty acids. Fatty acids are interesting. You can have these very, very long chains, and these chains can be like 20 carbon atoms. Big, big molecule. Well, actually not big. Proteins are huge molecules. Fats are medium-sized molecules, medium, small molecules. But still, you can get 20 to 40 carbons in a chain. It's pretty big. All right, so what we're going to do is let's look at some examples. We're going to look at, you know what was proposed? Toyota has proposed, and they have built this. Rather than burning methane, you know what they're going to burn? What's this called? NH3. Well, is this a binary molecular compound? Yes. So what we'd call it is element A just gets its normal name. So we'd call this nitrogen. And element B, we change the ending to "ide." But A is normal. And XY, we use the prefix. So we could call this mononitrogen, but oftentimes we drop the mono. And so we'll just call it nitrogen. And then how many? Tri, and then we don't call it hydrogen, we call it hydride. So this is called nitrogen trihydride. The way we write it is like this. But if we flipped it, you know, what's right side up or upside down in the world? If we flipped it, H3N, do you know what we'd call this? We call this trihydrogen, what? Nitride. In terms, once we know more about the name, it turns out that trihydrogen nitride would be a more accurate representation of this than nitrogen trihydride. But nitrogen hydride is according to the rules, but sometimes according to the rules isn't the most correct way of doing it. So what Toyota has proposed is, and they built an engine. This engine, rather than using methane or hydrocarbons, carbon, it uses ammonia. And so this, they tout this as having zero carbon footprint because there is no carbon. So when we burn ammonia, we're going to form, well, it depends on how thoroughly we burn it. We're going to form, rather than oxides of nitrogen, we're going to form oxides of, or not oxides of nitrogen. Rather than forming oxides of carbon, when we burn carbon, we're going to form oxides of nitrogen. Oxides of nitrogen are called NOx. NOx are very dreaded because when in the old days when you went for a smog test, they used to stick the detector in your exhaust pipe and then measure how much NOx emissions you have. And you know what NOx stands for? This stands for oxides of nitrogen. And what else are we going to form? And H2O, oxides of hydrogen. This one we already know. And so what are some examples of oxides of nitrogen? Well, it depends on the conditions, right? Just like the Bunsen burner, it depends on the conditions. If it's weakly oxidizing, you might form soot. You might form carbon monoxide. If it's strongly oxidizing, that is, you have more air going into the holes here, you should form carbon dioxide. So if it's weakly oxidizing, we might form NO.5. NO.5, is that right? Is it possible to have NO.5? No. This is where X equals 0.5. It's not possible. This would be a violation of what? Law of multiple proportions. This would be clearly. Because can you stick half an oxygen atom on a nitrogen? No. But since we write NOx, X is 0.5, it really is not NOx. It really is N2O. That's what it means. NO.5 means N2O. And once, Toyota also has the hydrogen car. Have you seen? Toyota's very innovative, I think. They have the ammonia burning car and they have the hydrogen burning car. Although not just Toyota, but a whole bunch of other manufacturers also have hydrogen burning car. And one of these promotional videos that I saw for the hydrogen burning car, this is, I think I was back in high school many decades ago. But back then, they took a beaker and they put it to the tailpipe of a hydrogen burning car, and there was condensate. And you know what they did with the condensate? They drank it. And I remember they actually drank it. And they drank it because when you burn hydrogen, what do you form? You form oxides of hydrogen. As long as it's not peroxide, as long as it's strongly oxidizing enough, it's going to be water. And so they were just drinking water. And then I thought, that's fabulous, So I always thought having a hydrogen-powered car would be fabulous. I was over at, it was like last semester, I was at Manhattan Village, and Toyota was there, and I was thinking, wow. And they were giving a Simple Greens, a $20 Simple Greens gift card for test driving their hydrogen-powered vehicle, the Mirai. So I test drove it, and it's just like an electric car. And I suppose if I put a beaker at the exhaust, I could drink it too, which I didn't do. But I thought that would be pretty cool. But the problem with hydrogen is it's so expensive. I heard people were complaining to fill up their hydrogen-powered car costs like $200, and the range is very short, and so it became very, very expensive to drive. So maybe ammonia is cheaper, maybe it's easier to make, and so this could be a good option. And so I've been thinking about this. If it were ammonia and they formed this, do you know what this is called? This is probably better known by its common name. The common name for this is nitrous oxide. Actually, it has other common names. Nitrous oxide is best known as laughing gas. So can you imagine that? You might, rather than put a beaker there, you might just get a hose and put it inside your car, and then that would be even better. Everybody would be laughing, I suppose. So this could be good, right? Could be good if you get nitrous oxide. But unfortunately, you might not get nitrous oxide. Depends on how it combusts. What are some other oxides of nitrogen that might form? Well, what's another name for nitrous oxide? Is this a binary molecular compound? Yes. So another name for this would be dinitrogen monoxide. Rather than saying monooxide, we drop one of the O's and just call it monoxide. Dinitrogen monoxide. What's another name for dinitrogen monoxide? Another name would be, depending on the charge on the nitrogen, if oxygen is -2, that means nitrogen must be what? Yeah, so we have 2 times X plus 1 times -2, 1 oxygen. At -2 has to add up to 0. Therefore, X is 1. And so the other name for this would be nitrogen with a charge of 1 oxide. I don't need the prefixes here. Why? I don't need the prefixes here because I can tell I need 2 of these nitrogens. Because I know the charge on oxide. What is the charge on oxide? -2. And 1 nitrogen is not going to be enough because 1 nitrogen only is +1. And therefore I need 2 of the nitrogens to balance out this because compounds are neutral. Ions are charged. And so compounds always add up to 0. And so here I wouldn't say dinitrogen 1 oxide or dinitrogen 1 monoxide. It's just called nitrogen 1 oxide because I can figure out the ratios based on the charges. But the most common name for this is this one, nitrous oxide. Are there others? Well, if it were just only nitrous oxide that forms, then this is good because there should be a way of capturing that nitrous oxide and then recycling it, maybe giving it to dentists or something like that. And then they can use it for their office. But we could also potentially form this. This one has a common name, nitric oxide. Nitric oxide, have you heard of it? What do you know about nitric oxide? Nitric oxide is poisonous. So you wouldn't want to capture the emissions off the tailpipe thinking you're going to get laughing gas because you might get nitric oxide. And so you should be careful. Nitric oxide is poisonous. Well, I need to take that back because nitric oxide is important. If we don't have nitric oxide in our body, it doesn't function properly. And so it's poisonous at high levels. Nitric oxide is very important in biological systems. And so you might know that, let me see. You might have known that nitric oxide won Molecule of the Year. Did you know that? In Science magazine. Science is the premier U.S. journal. It was quite a while ago. When was it? 1992. Since then, there have been many other molecules of the year. But the molecule of the year is nitric oxide, NO. A molecule of versatility and importance that has burst onto the scene in many guises. In the atmosphere, it is a noxious chemical. Noxious, this is one of the things that contributes to smog. But in the body, in small controlled doses, it is extraordinarily beneficial. It's extraordinarily beneficial for blood flow and for immune response. It helps kill foreign invaders. It dilates blood vessels. In other words, it has important functions, but like a lot of these things, actually there's one more here. This is the 1998 Nobel Prize. This is fairly recent because nitric oxide used to always be thought of as smog. You know, a lot of diesels emit nitric oxide, and cars used to emit nitric oxide in significant quantities. Much less so now. Smog used to be much worse. But anyway, it was primarily looked in terms of blood. And in fact, when COVID was happening, you know, there was a lot of problems with blood clotting. And so they were trying nitric oxide therapy to reduce the severity of blood clots at one time. And I think they met with some limited success. I'm not sure how successful those studies were. But that's nitric oxide. We do need it, but not too much. This would be smog. So this is smog. What else could we form? Well, what is this? Another name for nitric oxide? Another name for nitric oxide would be nitrogen, Roman numeral 2, oxide. Do you see where the Roman numeral 2 comes from? If oxygen is -2, that means nitrogen must be +2. That's it. Now, we've seen this Aus-Ich convention before. Aus refers to the lower charge, nitrogen 1. Ich refers to the higher charge, nitrogen 2. But the problem is this: is +2 the highest charge for nitrogen? No, what's the highest positive charge for nitrogen? What's the highest positive charge for nitrogen? +5. +5. So we could burn it a little bit more intensely to form something like this. What would you call this? We can't call it nitric because ich was the max. Maybe we should call it per-nitric, but we don't call it per-nitric. You know what we're going to call it? Well, there's one more name. I forgot to write the other name. If we follow the rules for the previous one, it's called nitrogen monoxide. And so nitric oxide, that's the most common way people call this, but if I follow the rules, it's nitrogen monoxide. If I follow the rules, what is NO2 called? Nitrogen dioxide. So most people will call this nitrogen dioxide. Give me another name for nitrogen dioxide. Another name for nitrogen dioxide would be nitrogen, Roman numeral, Roman numeral 4, oxide. I know the charge on oxide, I just don't know the charge on nitrogen because nitrogen's charge can vary from what to what? +5 to -3. And so I have to specify the charge on nitrogen since it has so many different charges that it could adopt. How did I get +4 or how did you get +4? You take one nitrogen at X charge plus 2 oxygens at -2. That has to add up to 0. And therefore X is +4. That's where it came from. So we could form nitrogen dioxide. Is it maxed out yet? No, it's not maxed out. And so I'm going to try to form nitrogen trioxide. This is going to be called nitrogen trioxide. Now surely it must be maxed out. What's another name for nitrogen trioxide? No. Nitrate has a negative charge. And so this is an ion. Ion has a different set of rules for nomenclature. This is nitrate ion. However, this is nitrogen trioxide. It has no charge. It's zero charge. So nitrate and nitrogen trioxide are not the same. They are not equal. And so give me another name for nitrogen trioxide. Nitrogen, Roman numeral 6, oxide. Okay, now we must be maxed out. Are we maxed out? So what do you suspect about nitrogen trioxide? Do you expect nitrogen trioxide to exist? No. We do not expect this to exist. Nitrate, we do. Because nitrate, there's no problem. We have 1 nitrogen at X plus 3 oxygens at -2. This has to add up to -1. Therefore, X is equal to what? +5. +5 is okay. So nitrate, not a problem. Nitrogen trioxide, big problem.
So does nitrogen trioxide never happen, or is it just unstable?
No, it doesn't happen. I mean, it could happen. It could form like, I shouldn't say, there could be a peroxide link, you know, that's possible. And so let me put a little asterisk here. There could be a peroxide link, but if there's a peroxide link, then what that means is the nitrogen stays at +5, the oxygen changes from -2 to -. Do you know what peroxide is? What is the charge on each oxygen in peroxide? Peroxide is O2 2-, means each oxygen is -1. Each oxygen is -1. So what could happen is, yes, we could throw in more oxygens, but some of those oxygens have to be linked together like a peroxide. And peroxides are highly unstable. But the nitrogen is not going to go to +5, go beyond +5. So what we have to do is we have to come up with other ratios. So let's take a look at some other ratios that we see here. N2O2. What do you call this? Dinitrogen dioxide. This would be nitrogen 1. What would you call this? N2O4. Dinitrogen tetroxide. Could we have N2O5? What would that be called? This is dinitrogen tetroxide. Tetraoxide or tetroxide? Either. Going. What's this one on the bottom called? Dinitrogen pentoxide. Should I keep going or should I stop? Should I stop here or should I keep going? I can't go any farther than this. I have to stop here. There's another way. If you don't like algebraic equations like this, then do it this way. Each oxygen is what? And how many do I have? 5 of them. And so 5 of these negative 2 is going to give me a negative 10 total charge. And then I have 2 nitrogens at X. What is X? X has got to be plus 5. So if I have plus 5 here, that's going to be plus 10. And so plus 10 minus 10 gives me 0. Compounds are neutral. So this is nitrogen 5. I need to stop here because I'm at max. Nitrogen, Roman numeral 5, oxide. Are we out of time now? No. What time? Huh? We go to 40? All right. 20 minutes left. Okay, nitrogen 5 oxide. So this is why people just call it generic NOx. They call it NOx because who knows what's going to form. You're going to get a mixture of these things. And the problem is this. All these are what's considered smog. And so, yes, this has a 0 carbon footprint, but what are we going to do about all these NOx emissions, which are all poisonous? So do you think this ammonia burning car is such a good idea? Well, they're getting rid of the CO2, but they're replacing it with NOx, NOx. But you know what they say? They say, well, the NOx is not a problem because in a catalytic converter, what it does is it converts the NOx into nitrogen. And so this is how we can have it. An ammonia burning car without heavy pollutants. Now, it depends on how efficiently the catalytic converter works. The catalytic converters aren't so efficient. Diesels, diesels are notorious of producing a lot of NOx. And Mercedes and Volkswagen came up with some great ideas. For Mercedes, they had something called Blue Tech. And Blue Tech was the solution they injected into the exhaust to react with the NOx. And what it did was it converted the NOx into nitrogen. But unfortunately, it wasn't efficient enough. So they could get it to pass all the California emission standards if they detuned the engine. And so the engine wasn't running normally. But when the engine ran normally, then it generated too many NOx, and they weren't able to get rid of it. And so this created a big scandal in which whenever, like, the Volkswagens were tested, they detuned it, and then when they were on the road, they retuned it because it wouldn't be very good to drive, and it was caught. I think California Air Resources Board caught it, and so now you can't buy a diesel passenger car anymore because the emissions aren't good enough. And so it'll be interesting to see what happens with this ammonia, because this ammonia burning one will produce way more NOx than the diesels did. And so we'll see. All right, that's binary molecular compounds. The next one we're going to look at are ionic compounds. Naming and writing the formulas for ionic compounds is fairly straightforward. For ionic compounds, we write the cation first, and so we write the cation name, and then we write the anion name. And so, we just put them together. And so all we have to know are the names of the cations and names of the anions. The anion names we pretty much covered, but there are some cation names that you have to memorize. Most are off the periodic table. And so the ones off the periodic table, we don't really have to do much memorization. We can figure out the charge off the periodic table. There are 2 that you have to memorize, and these are 2 polyatomic cations. One is ammonium. Ammonium and ammonia are different. And so this is ammonium. And the other one is this. is this mercury 1 or mercury 2? Hg2 2 plus, is that mercury Roman numeral 1 or mercury Roman numeral 2? It's mercury 1. The Roman numeral comes from the charge on each mercury. And if I have 2 mercuries with a total positive charge of +2, that means each one must be +1. +1 adds up to +2. And so this is called the mercury 1 ion. So you have to memorize these. There's another one, hydronium, but we're not going to worry about it right now. We'll worry about it later. And so add these 2 to your list of just straight memorization. Okay. So we can look at some examples. Now, ionic compounds are different than molecular compounds because of the structure. Molecular compounds tend to form molecules like water, H2O, or hydrogen peroxide, H2O2, or carbon dioxide, CO2. Whereas ionic compounds, structurally, these form lattices. And so it's a bit different than this. So let's take a look at an ionic compound like this. How would we name Na2SO4? Well, the way we name it is we name the cation first. What is the cation? Sodium, or sodium ion. And then we name the anion. What's the anion? Sulfate. And so this is called sodium sulfate. But why don't we call it disodium sulfate? We don't call it disodium sulfate because we could figure out how many sodiums we need because we know the charge on sulfate. The charge on sulfate is 2 minus. Therefore, how many sodiums do we need? 2. And so it's not necessary to call it di because we can easily figure it out because all compounds are neutral. They have 0 net charge. Now, when we look at it, it doesn't form molecules. We don't see molecules of sodium sulfate. Instead, what we see is a lattice. So let's say the small circle is sodium, the big circle is sulfate. And so a lattice is like this. It's like tiles. If you have a tile floor, is there a molecule tile? Let's say we have a tile floor that looks like this. This is a pretty bad drawing, but I think you get the point, maybe. Is there like 2 small tiles and 1 big tile that we can call a discrete molecule? That's an intact unit that's not broken apart? Or do they all kind of blend into one another? In other words, which of the big circles does this black one belong to? Does it belong to the one on the right, or does it belong to the one underneath, or does it belong to the one on the left, or above, or on top, or below? They're all sharing it, right. And so it belongs to all of them. And that's what we have in an ionic lattice. Whereas in water, this hydrogen belongs to which oxygen? If I look at this hydrogen, does it belong to both oxygens or just one oxygen? Just one. And so this is what we call a discrete molecule. Whereas when I look at the sodium, well, I don't know, it belongs to all of them. And so this is what we call a lattice. And so it forms a slightly different structure. This is what, and more specifically, it's called an ionic lattice. So we need to know the names of the ions, and so let's continue a little bit of review for the ions. The ions we have to memorize, the anions. And so there are some that you have to memorize. There's some that you get off the periodic table. And there are others that we derive beyond the periodic table. So, for example, this one is called This is called hydrogen carbonate, or another word for this is bi. This bi does not mean two. This bi means we have what's called an acid anion. And so acids start with H. And anions are negatively charged. And so it's an anion that starts with H, bicarbonate. This is not an acid anion because it has no charge. This is what we call an acid. The acid name we'll talk about later, but let's look at some common acid anions. The common acid anions would be this, HSO4 minus. Do you know what this is called? This is most often called bisulfate or hydrogen sulfate. HSO3 minus, do you know what this is called? Bisulfite or hydrogen sulfide. Mm-hmm.
About the lattice structure, so they're sharing electrons, right?
No. They're not sharing electrons in an ionic lattice. There's another type of lattice called a covalent lattice in which they're sharing electrons.
So what are they doing?
Sodium has a charge of what? And sulfate has a charge of? What they're doing is there's a Coulombic force of attraction that's going to be proportional to the charge on the sodium, which we call A, the charge on the sulfate, B, divided by the distance between the centers, squared. This is called an ionic bond. This is the force for the ionic bond. And so we could calculate the force of the ionic bond. The ionic bond is what's holding the ions together. So that's what they're doing in the lattice. You know, we could just use Coulomb's law to figure out how strong the ionic bond is. Okay. All right, so there's some others. HPO4, 2 minus. This one is called monohydrogen phosphate. It's not called biphosphate. The reason it's not called biphosphate is because we also have H2PO4 minus. This is called dihydrogen phosphate. How about trihydrogen phosphate? Well, trihydrogen phosphate is an acid, and we have a different set of rules for acids that we use. And so we have these ions too. And so what we're going to do is we'll take a look at some examples of naming. Actually, let's take a look at the rules for naming acids next. For acids, we only have 3 rules. If the anion ends in 8, then the acid is named ic acid. If the anion ends in ite, then the acid ends in aus acid. And if the anion ends in ide, then we use a hydro prefix and the ic acid suffix. And so let's take a look at some of the acids that I said. H2CO3. H2CO3, the anion ends in 8, carbonate. All acids have the same cation. The cation here is H plus. And therefore, the acid name is going to be carbonic acid. If we look at this one, H3PO4, the anion is phosphate. The cation is always the same for acids, H plus, and therefore the acid name will be phosphoric acid, but phosphoric acid hasn't been used historically. Historically, people have called it phosphoric acid. And so that would be phosphoric acid here. And then there's one more rule that I need to finish up here, and that is something called hydrates. And so let me do that here since I don't have another page. Or maybe I do have another page. No, I don't. CuSO4, what do we call this? Well, we have to name the cation. The cation is copper, but copper has two charges. It's either copper 1 or copper 2. Is this copper 1 or copper 2? This is copper 2, so it's going to be called copper 2. And the anion name? Sulfate. Copper 2 sulfate forms a lattice, so we'll have copper ions, sulfate ions. This. And water molecules are tiny. So what can happen is a water molecule can sneak in and get in between the ions here and get stuck in the lattice. So the water molecules can squeeze into the gaps between the ions and create something called a hydrate. And if we fill in all the gaps, then we end up with this compound. This compound is copper 2 sulfate dot 5H2O. And this is a solid, so it gets stuck in the gaps there. And the name for this is copper 2 sulfate pentahydrate, penta for 5, or 5-hydrate, or I think we can spell it out, 5-hydrate. Because is there water and air? Yeah. And so what happens is the water is moving around, and eventually it's like dust. You know, if you have tiles, eventually some dust will settle between the tiles if there's a gap. Right? Just randomly happens. And so this just randomly happens with water. Water will get stuck in the gaps between the ions. So this is copper 2 sulfate pentahydrate. It looks well hydrated. It's still a solid. But you know what this is? This is copper 2 sulfate dehydrate. We don't call it dehydrate, we call it anhydrous. And so if you take this stuff and bake it in the oven, you get this. But if you leave this sitting out in the room, what happens is if there's any humidity in the room, the water molecules hit the surface and then squeeze into the little gaps in the lattice and hydrate it. And so it's a process. So you start off with this, which is the anhydrous, and eventually it starts to hydrate. And here it becomes fully hydrated. And so it's not wet, but the crystals have water stuck in there. And you can drive out the water. All we do is throw this in the oven. If you want to dry this, throw it in the oven and dry it off. That's the hydrate. So the best thing to do for nomenclature is to do a lot of practice. I assigned a huge homework problem set, like 60 plus problems, 66 problems I think, and multiple parts. Like one question has like 20 parts to it. So it's kind of crazy. But what you should do for something like that is you should do all of them, but you might not have enough time to figure all of them out. So what I would do is if you're running out of time, just write the answer. So just copy the answer from the solutions manual, and then you review it multiple times. And by reviewing it, the more you see it, the more comfortable you'll feel, because you'll start to become more familiar with these. And you can see the patterns and nomenclature rules when you see a bunch of these examples. We'll look at some examples tomorrow, because we're out of time today.